All right, take it away.
Hello, everybody. Can we just give a round of applause to our organizers? They're amazing. Thank you so much, guys. The audio and video, can we give them a round of applause for their work here? Thank you so much, guys. Hey, so today I'm going to speak about how to sleep at night having a cloud service. The alternative title of this talk is to Common Architecture's Do's and Don'ts. You want to deploy a service, any kind of service. One person shows up. Two people show up. 1 million people show up. What do you do now? I like to sleep at night, knowing that my cloud application is secure and I'm able to rest with my users happy. So I'm going to teach you that, or I'm going to try at least. There's one simple hack you can all do to actually get to sleep at night. Just let it burn and go to sleep. Forget about it. Thank you so much. Bye. And okay. So a little bit about me. I've worked over 10 years in software development. I've worked on backend services for millions of people. When I was in Microsoft, I worked for OneNote services, doing services for nodes for millions of people. And now I work in Snowflake, doing developer productivity. So everything from CI pipelines to tests to development environments. I do all of that. And I'm going to teach you some general concepts. Compared to some of the talks here, this is not scientific. This is not backed by evidence. It's just what I've seen works for big companies that I've worked for. Things that I've seen applied, fundamentals I've seen applied through all these companies. And we'll separate them in 4 levels. We'll talk about easy, medium, hard, and expert. Let's talk about easy. And it's not that it's easy, but it's more than it's quick to apply, and you get the most value out of this. Let's talk about infrastructure as code. What is infrastructure as code? When I started in this field, I used to deploy directly to prod. Did anybody else deploy directly to prod at some point in their lives? Show of hands. Wow, I feel brave. But if I forget something, prod will die and crash and burn. And I didn't like that. So the first solution is to create a script that you pass through any kind of engine, and you create a cloud architecture. Right? So every time you want to deploy something, you have a given set of machines, a given set of instructions to generate a cloud environment. And that way, it's reliable. You can trust it. The second level is identifying all your network connections, ingress and egress points, and explaining how that would look so that you can always reproduce your deployment. You can always try it again and try it again. And the third level is building your own containers, right? Building your whole infrastructure from the ground up, and you know that everything contained in your infrastructure was put in there for you. So this is about packages that you trust. This is about demonstrating to your customers or to regulatory agencies that you can provide all of this. If you want to try infrastructure as code, try Chef, Puppet, Ansible, Terraform, or anything cloud specific. You can use any cloud out there. You can provide a set of instructions to deploy to your environment, and you can put them in Git. So if one developer changes the environment, we can know exactly who changed it and for what reason. We can have pull requests, and we can have gated automation on these scripts. So that's why we want to have infrastructure as code. Let's go to the next topic. CI/CD. I'm in Devops days, so hopefully everybody is familiar. But let's think about a world without CI/CD. Developers want to integrate code into their environment, and somebody introduces a bug, which breaks everybody out there. What happens? Everybody else has to wait for that one developer to fix their code. And then if everybody's waiting, we're wasting money. Developers are expensive. Also, we don't want to have them like that. And then we have to wait for the fix to go in, and once the fix go in, now everybody can do their work. What's the solution? Well, if a developer wants to merge, we want to do first some tests before commit. So when you type git commit in your terminal, you get a set of checks. This is commonly called pre-commit checks. So you do a git commit, and in here you can enforce your linting, your standards, empty files, null spaces, all those pesky things you don't want to catch later. And this is local, so the developers can iterate on their commits until they have exactly the linted and formatting you want to have. Or you can also check for secrets here. But you also have to be careful, because if you do git commit and you pass the flag in, you can skip all of these pre-commit checks. So it's just nice to have for the developers. What's the next step? CI. After they add a commit and they have their own branch, we check again. Linting, tests, secrets, everything we want to enforce, we can test it now on CI. Then the last step, we went too fast. Too fast, okay. The last step is after merge. Unless you have a policy which requires that every merge is updated, the result is that after you merge, you could have different code than what you had in the branch. So after you merge, you also have to make sure your code works. You can do a light set of build, a light set of tests. Some other companies do bigger builds and bigger tests. But the idea is that you have this comprehensive CI environment where you have before commit, locally for the developers to test, in CI, so once the branch is published, and then after they merge, we make sure that it's complete. This way, you avoid most breakages and you save the most time. And you also want to think about the earlier you catch these mistakes, the less they cost. Because by the moment it's merged, by the moment it's released, it's too late. You already have to have all the developers waiting and for this to happen. So you just be conscious of that. And then talking about the continuous deployment, CD, you always want to deploy constantly, because the time you take to deploy is the minimum time you're going to have to fix a mistake you did in production. So if you ship every hour, the fastest time you can fix something in a code defect is an hour. If you ship every week, the fastest time you can solve something is in a week. So yeah, there's some configuration issues we can solve, but what happens if you have a code defect and it's affecting your 1 million customers? Okay, so if you want to try out CI/CD, ask your doctor first, but then go to GitHub Actions, Jenkins, Circle CI, Travis CI, and try it out yourself. Let's talk about alerts. We could talk about alerts and how we could put CPU, memory, network, certs, request per second alerts. But alerts don't let us sleep at night, so we'll skip to the next topic. Okay, load balancers. We're going to talk about load balancing because it's one of the most effective ways I've seen in my career. A properly configured load balancer can serve multiple organizations. So we have a server, which we do requests against. If the server gets sad, we cannot do requests against it, right? So what do we employ? We employ load balancing, which is more servers, so a little bit more money, but it chooses one of these 3 servers to route the request to. If ever one of the servers gets sad, we can stop serving requests to that server, and then take it out of rotation, take it to the other 2, get other machines, and then we can wait for that server to come back alive or get a new server, and then serve to them again. This is a common practice, but you'd be surprised how many organizations don't have this. Just having the most basic set of load balancers change an organization. If you want to try it yourself, you can try Nginx, which is one of the most common ones, or there's a cloud offering of choice on every cloud. Let's talk next about UUIDs, universal unique identifiers. And I also challenge you to think about this problem. So let's say we have a like server. Let's say we're in some social media platform and we want to implement a like server. A like comes in to our browser. Our load balancer routes that to a VM. The VM routes that to a database. Database writes everything, comes back to the VM. The VM brings it back to the load balancer, the browser to us. Let's say something fails. My manager comes to me and asks, hey, why did this like didn't go through? If I have this architecture, it's really hard to tell because I have millions of likes. Right? I have thousands of millions of likes. I can't know why that like didn't succeed. So Cloudflare and a lot of teams do this thing called CorrelationIDs, request IDs, unique identifiers. And they're atomic transactional identifiers that identify a single transaction. So what does that mean? So if when we start from a client, from the browser, we generate an ID. In this case, we'll say A1. And from the client, we'll propagate that ID through every service it touches. So we'll see A1 being propagated and now written to our logs. We see it propagated to the database. We see it propagated back. We see it propagated all the way through. And our logs now look like that. And we can now join our logs and see what happened in all of these different places. Right? So if my manager comes and asks me, hey, what happened to A1? I know it succeeded because I can do a join or combine all these logs and know what happened with A1. And if something tends to fail in A1, I now have the breadcrumbs. I can follow the breadcrumbs to get to what happened with the A1. OK, so if you're going to implement this, there's no specific library for this, but it's just that every time you start a transaction, it could be a payment, it could be a user-generated flow, it could be an API request, assign a unique ID to it so you can trace it throughout your systems. Even if you're in a monolithic architecture, it's really useful. Let's go to medium, where things start getting spicy. Let's talk about centralized logging. So we talked a little bit about doing a join on our logs. If we have a system that looks like that, like this, we have queues, we have VMs, we have workers. They all generate logs. And let's say you have an issue. The like didn't get propagated. Payments are not going through. Are you going to go look in every log? No, so that's why we're going to invent a log server in which we can route all of the logs of all of our applications and consume them in one single spot. So then all the logs from our like example can go in a single table or in a single instance. And now when I look, I have the entirety of the A1 transaction breadcrumbs, and I can trace back my mistakes. OK, if you want to try this, we can talk about the elk stack. And the coolest thing about this is the E in elk stack are actually back there. They have a sponsors booth. So go talk to them if you want to start getting to decentralized logging, which is Elasticsearch, Logstash, and Kibana. Elastic Cloud is actually there, so go talk to them. You can also try Grafana, Spark, or Prometheus. But it's really cool that they're close to us, right? OK, let's talk about the next thing, which is health checks and automation. When we have our VMs, and this is less relevant a little bit now with Kubernetes, but we're going to talk about health checks nevertheless. Our robot asks whether the VM is OK. The VM says it's OK. Every minute, every 15 minutes, whatever time span you think is adequate, our little agent can ask if everything's OK. And the VM will come up with how it is. You can use CPU, you can use memory, you can see requests per second. You can use several metrics. But when the machine says it's not OK, you can put these agents to reboot the machine, to destroy it and create a new one. You can ask him to go out of rotation of the load balancer. You can inform the load balancer that this machine is on. Plenty of load balancers even have health checks integrated into them. So think about that. And then when the machine comes back on, you can continue with these health checks. So it's important to have these in some kind of way in your application. Especially because after you do this, you can automate some of the tasks. If your machine is running high on disk utilization, maybe you can give it more disk, right? Or you can swap the disk for something else. So, and that lets you sleep at night. Yeah. Let's talk now about auto-scaling. If you have a system, we're going to say we have 3 VMs serving requests. And this is the blue line is the maximum requests per second that the system allows. If we only have this amount of resources, all of the requests that exceed that resource will be dropped, or it could be put into a queue, but they could be dropped depending on the scenario. Auto-scaling is the fact of adding more VMs as load increases or decreases, and removing VMs as load increases or decreases. You can have 2 types mainly of auto-scaling, which is auto-scaling based on the length of the queue you have of work to be done. You could do auto-scaling based on resource usage. And you can also add some heuristics here. Like if you know that your customers are from Monday to Friday from 9 to 5, you can add some heuristics to your auto-scaling to actually prevent requests being dropped or save money. So auto-scaling is one of these concepts that is important for you to help you sleep at night. Let's talk about the next concepts, and these are hard concepts or expensive, or both. Let's talk about green-blue deployments. So when we're deploying constantly, as we talked every hour, there's this question of how do I serve the new version of my software to my users? I have version 1.0 and I have version 1.1. All of my users are in version 1.0, but I need to migrate them. How do I do that without any downtime? Well, the answer is to create 2 identical clouds. And if you did the first step, infrastructure as code, this should be easy, quote unquote. So you create 2 different clouds, and you slowly start to migrate the traffic from one to another via load balancer. And then as the traffic grows, you do these health checks on the cluster to see if the traffic is being handled properly. So in here, we see that version 1.1 didn't work, has an issue. So then we roll back to version 1.0, and then we wait for the next version to come in. In this case, version 1.2. And then once version 1.2 comes in, we can slowly repeat the process of slowly migrating traffic from 1.0 to 1.2 until all your customers are now migrated to this. And you didn't even have to wake up at night. You didn't have to do anything. It should be automatic, and rollbacks could be automatic. Let's talk about expert mode. And in these ones, these are expensive things. You probably shouldn't try unless you know what you're doing. They're expensive and complex. So anomaly detection. If you have a good set of data of how your outages happen and how the graphs of your outages happen, you can apply machine learning and statistics to figure out what happened before that or whether that's going to happen again. This also happens a lot in manufacturing. In manufacturing, they have a lot of sensors detecting the machines to see if there's a wobble. If there's something that indicates that the machine is going to fail, and they try to do predictive analysis to know whether the machine is going to fail. You can do the same thing with VMs because we have thread pools, we have memory. You can think about it with CPU. If we go over our allotted CPU, we could have an outage, but it also happens with memory. If we see a steep incline in memory usage that's heading towards and this could happen as a garbage collection event. This could happen as a heavy application. This could happen with a thread lock. And this event it will help you alert you when it's going to happen, or have automatic corrective action. So if you know the VM is going to run out of memory, or your cluster is going to run out of memory, you set rules to prevent that from happening. I'm not going to say which company, but usually they reboot the VM before this happened, and then it'd be OK. Maybe not the best of solution, but it works. You can also set alerts, but alerts don't let you sleep at night and require manual intervention, so we don't like them. And then we're going to talk about the last point here, which is idempotence. And I think this is the most important point, and it's the hardest to get right. Let's talk about idempotence. Imagine you have this app called Denver Pay, in which you can pay somebody $200. We have a REST endpoint, which is an HTTP post in /payments. If you pay $200, it gets deducted from your bank account, and then you have $400, right? Now, what happens if you click the payment link twice? Like, let's say you double tap the pay button. We have A, it should happen twice, and then you have $200. Or B, it happens once, and you have $400. Who says A? Who says B? Who says, I don't know? Awesome. So idempotence is the property of certain operations in mathematics and computer science so that they can be applied multiple times without changing the result beyond the initial application. Now, this is heavy text. The way I think about it is a SQL query. If you run this SQL query, which is update students, set first name equals John, where ID equals 123, the first time you run it, it will update the record. But the following 4 times, you won't do anything. So we can say this is an idempotent request. So let's talk about how we could do this in our payment system. What some companies as Stripe do, or other things do, is to set an ID for the request generated randomly when the page loads, so that that's attached to every post request to the payment gateway. And then on the payment gateway, we keep a database or an in-memory map of which IDs we've seen before. So if we want to execute a transaction that with an ID we've seen before, or we're processing a transaction with an ID we've seen before, we stop it and we just say it's been accepted or it hasn't happened yet. So that way you can guarantee, quote unquote, that a payment is only going to happen once. You can think about idempotence in plenty of different ways. If you have to write to a database and make sure that things only happen once. Let's say a mailing list. If you want to send out a mailing list on a server, you only want it to happen once. You don't want your customers getting 2 emails at once. So idempotence helps with these scenarios, and designing your systems to be stateless and idempotent will save you more headaches than you can possibly imagine. But it's also a really hard technical problem. And then we can also talk through a lot of things. We could talk about fault-tolerant applications. If you shut a VM down, it should be able to just create another one. We could talk about chaos engineering, where we randomly shut down VMs so we test the resiliency of the system. We could talk about orchestration platforms. We can talk about observability, but I'll let you all go find out about that. And I wish you, with all these architecture tips, that you get to sleep at night somewhat within the cloud platform. Thank you.
All right. Questions? Are we just going to listen to the rain now?
Awesome.
All right.
I do want to answer one question. I did draw all of these slides. So, yeah, because that was the question from the previous presentation.